All right, everybody. Let's talk about lesson 3 here, addition and subtraction of those rational expressions. We talked before about non-permissible values. We talked about multiplying and dividing them, and the process we went through to do that. Factoring really is going to help us. When you think about addition and subtraction, in terms of fractions first, well, there was something I needed before I could add them together, and the same strategies will work here with rational expressions. And really what you needed in order to do this was a common denominator. Now the same rules are applied here as well, you just have variables to think about. So before we do that, think about how this worked again with just two rational numbers before we talk about a rational expression. So I can't freely add these fractions together right now. Their denominators are different. Right, the base size of each one of those pieces of that fraction, well, they're different sizes. I can't really compare them. In order to compare them and combine things, they really should have the same denominator. So I can alter them as long as I remember that in order to keep a fraction equivalent to its original state, whatever I do to the bottom part of it, I have to also do to the top. In other words, if I change the numerator, I have to change the denominator by the same amount. So my common number between 3 and 4 is really 12, right? That's the lowest common multiple between them. Now, it's not the only common multiple between them. I could use 12, I could use, well, what else would work? 36, I could use 48, any of those. 24 is another. But if you think about doing the lowest common denominator, well, you don't have to reduce and simplify at the end. That really is the only step it saves you. So if your brain sees another common number first, it's not necessarily the lowest, that's okay, and we can reduce them at the end. But 12 will work, and I can change the first denominator from 3 into a 12 by multiplying that 3 by a 4. Now what I did to that denominator, I also have to do to the numerator to keep this fraction equivalent. So I need to do that for the first fraction, but the second fraction changes by a different factor, and I'm going to need to multiply both the top and the bottom by 3 in order to get us to our 12. And I keep them color-coded just for this first one to really illustrate the point that, well, now I have two just separate fractions, each of them now with a denominator of 12, and that really alters how much I had before in terms of the original pieces in my numerator. The amounts really are the same, it's just the size of that piece that we're talking about is now different. So really I've got 17 over 12. 17 pieces that are each 1/12 in size. And you could represent that as a mixed number as well, but an improper fraction is perfectly fine for what we need. Okay, so I'll do that again with the other one beside it. Between 6 and 9, you can use a common number of 54. So I can multiply the first fraction, every part of it, by 9, and the second fraction you can multiply every part of it by 6. Okay, and that will work just fine. You could also think about a smaller denominator between them. 18 would work also. And so I might have to reduce this in the end, but that's all right. So I've got 9 minus 42, whole thing divided by 54. 9 times 6. And that will leave me with, I don't really want to mess this number up, so let me just type it in my calculator here real fast. 9 minus 42 is 33, but negative over 54. Now, that's probably a number divisible by 3 if I'm going to look for a common factor between them, which it is. So in terms of a lowest, most simplified fraction in lowest terms, negative 11 over 18. Now, I could have avoided that whole last step of reducing it by just, instead of multiplying the first fraction by 9, I could have multiplied by 3 instead, and then the second one by 2 to make my denominators 18. Still gets me to the same place anyways, so it doesn't really make a difference which method you choose. But you can do this with variables also. Now, as long as my denominators are the same, I can freely add these fractions together. So this is a nice one. I can add my numerators 1 plus 2 to get me 3, and it's, 3 over 2a. No lowest terms reduction needed. I'm done. That is already lowest terms as best I can make it. For the second one, I can't freely add them together right now because one denominator is m, the other is m squared. They are not the same thing. The exponents on them are different. So I think about making them the same thing. Well, I can take the first fraction and multiply both the top and the bottom part of it by m. Right? The m multiplies with m, that'll give me m squared, but I don't need to change my second fraction because its denominator is already m squared. Right? So I don't necessarily need to change both. I could only alter one fraction if needed. Let's zoom that like that. So we'll get 5m over m squared plus 4 over m squared for our final simplified answer of 5m plus 4 over m squared. And sometimes students get tempted to take the m's that they see in that expression and simplify them, in the sense, well, what they want to do is cancel one of the m's, like divide it out with one on the bottom. But I can't do that because both terms in the numerator would have to have an m, and really I really would want an m squared if I'm really going to want to simplify things fully. So I can't just divide out m's wherever I choose to. Okay, it doesn't work here mathematically, so I've got to leave it just in that form in the box. And you can even do this with multiple variables, right? I'm free to multiply by whatever I want, as long as I keep things equivalent. So if I'm going to think about a common denominator here between those two denominators that I have that are different, well, a 2mn is something I can achieve. And I can alter both fractions. If I multiply the first one, both top and bottom, by n, that'll get me 2mn in the denominator. And the second fraction, well, I can multiply by the only thing missing to make that happen. In this case, it's 2m. And now both my denominators are going to say 2mn, which will satisfy my requirement for a common denominator, and I can just adjust the tops as I go to combine them, which will allow me to freely subtract these fractions. So the first one ends up being n over 2mn minus 8m over 2mn once again, and I can subtract now n minus 8m over 2mn as my final simplified fraction. Okay, again, a common denominator is what's needed, just like it was before. Okay, so as long as I know that, well, what happens if my denominators are a little bit more complex, right? What if they're not just one term? What if they're, what if it's two terms? What if it's a binomial? What if I've got multiple variables and higher exponent powers? What if I have coefficients? We can take care of all of this as well. And if you think about this, it's very similar to how you found a lowest common multiple previously with breaking something down into its prime factors. Now, some people are going to be very good at doing this just, by looking at the exponents and the variables and the coefficients that are there. People are able to see those connections right away. But this little method will help you figure out, where all the pieces tend to come from. Okay, so I'll tell you how it works here, but we'll do the more, we'll do another method as we try some of these problems out underneath, where it tends to be a little bit quicker to do this. But if some people need the whole breakdown of this, the way it works is we're going to list out all of the factors of each of these expressions, and our common multiples can be built by taking the highest powers of each of the factors that we're going to see. So if I break down 12xy, well, really that's the same thing as saying 4 multiplied by 3, which is 12, and 4 is the same thing as 2 squared, right? So 2 squared multiplied by 3 multiplied by x multiplied by y, that'll give me my original 12xy. Now we can do the same thing for 8x cubed times y. Now 8 is the same thing as 2 cubed. So let me write this one out here. 8's 2 cubed. There's no 3 that's in it. There's x cubed, and there is a y as well. So I've factored into its smallest pieces. Now the lowest common multiple can be built by taking the highest power of each element. So if I compare the 2's, the highest power of 2 I have is 2 cubed. So I'm going to take that one. For the 3's, only one of them has a 3, so I'm just going to take a 3. For the x's, I have a choice between either taking x as part of that common multiple or x cubed, and I'm going to take the highest power, so x cubed. Same thing for the y's. If they're both y to the power 1, I'm just going to take a y. And if I multiply all of those purple elements back together, well, 2 cubed is 8. 8 multiplies with 3 for 24. And I've got an x cubed y. Okay, so there in purple is my, my lowest common multiple. The first time that these two terms will really match up in terms of giving us a common multiple. And what we really care about, a common denominator. Now I can think about this differently. If I look at the numbers of 12 and 8, their multiple, the first one is 24, right? I can do 12 times 2 or 8 times 3. So that'll work. In terms of the x's, well, 12xy is missing a couple x's to get to x cubed. So I'd have to multiply this by x squared to get to x cubed, but I can get to x cubed. That's the important part, which is why it's part of my common multiple. Same thing with the y's. I don't have to alter them, so it's going to have a y in there as well. So if I just look at the two terms for the second one, well, 15 and 2, their common multiple is going to be 30. The first one has an a cubed. The second term has just an a, so I know I'm going to be able to get to a cubed if I multiply the second one by a squared, right? That'll make my exponents work out. I could also get to b squared as well. I can multiply by b squared if needed, and I can include a c as well to make them, a common multiple between them. So that's what I'm going to get, and if I do this the same method as I did before, I'll show you that it actually works. So 15 you can write as 5 multiplied with 3. The a's will keep together as a cubed, b's will keep together as b squared, and well, here's my 2ac. Right, there's my two terms that I'm working with. And we said if we take the highest power of each element that's there, highest power of each factor, I can get my common multiple. So I need a 5, there's only one. I need a 3, there's only one. I need a 2, there's also only one. For the a's, I'm going to take a cubed. For the b's, we're going to take b squared. And for the c's, we'll take c. And if you put all of those together and you multiply them, there you'll have your common multiple anyways, right? 5 and 3 make 15, multiply with 2 for 30, and all your variables are present as well. So either method you choose, by visual inspection or breaking them down into their parts, either one will give you the same results. So I can put this into practice down here when I try to add these two together. Now if you look at those denominators, they're very different this time. There's coefficients to think about, and there's also variables. And if I think just about, what common multiple I want to use here, or a common denominator, well, 3 and 2 share a common multiple. Like I can get to 6, and I could also get both of them to x squared if need be in terms of the variable. So that's the common denominator I'm going to try to work with. So if I alter the first fraction a little bit, well, it's got a 3x squared on the bottom. I want to make it into a 6x squared. So I'm going to multiply the first fraction by 2, top and bottom, to make my denominator 6x squared. And if I do something similar to the second fraction, well, I've got an x over 2 this time. If I work with the denominator first, I want to turn that 2 into 6x squared, so I need to multiply it with 3x squared. Again, top and bottom, to keep that fraction equivalency. So if I write out this statement again, so I've got 10, now the denominator is 6x squared, plus 3x cubed over 6x squared. Again, the goal was the same, to make the denominators the same thing in order to actually combine and add these fractions. So I'm going to end up with 10 plus 3x cubed over 6x squared as my final result. Common denominator of 6x squared. All the other rules are still true. I just have to find that denominator using variables. And again, you can try this with multiple variables as well. So think about between 6 and 15, what numbers they may have in common. 30 is a common multiple to them. So let's write this off on the left side this time. So common denominator. I want to get to 30 because I can do that with 6 and 15. If I look at the x's then, x squared seems reasonable because I can multiply the first denominator by x. So at 30, x squared seems good. And I can also multiply the second denominator by a y to include that part. So 30x squared y is what I'm going to aim for as I make this denominator. So the first fraction is going to change as I start to multiply things. And, to make it 30x squared y, well, I have to multiply it by a 5 and an x, top and bottom, to make that work. For the second fraction, I don't have to multiply by nearly as much, in the sense that, it's a little smaller, right? 2 times 15 will get me to 30, and I can include the y as part of that factor as well, right? So I'll multiply the second one by a factor of 2y, the first one by a factor of 5x, and then I can see my denominators will become the same. So the first fraction changes into 5x as a numerator, but now 30x squared y as a denominator, minus 4y divided by, again, the same denominator, 30x squared y. That's the goal, right? Make them the same, and now I can subtract them to finish this off. So I get 5x minus 4y, whole thing divided by 30 x squared y. So all of the same rules apply when it comes to, you know, rational expressions, right? They really are just fractions. They've just got some variables to think about. But other than that, really nothing changes. Okay. Now I can simplify an expression that looks like this too, again, as long as I remember that the rules don't change. In order to subtract these two different fractions, I need a common denominator. Now, the new denominators are just numbers here, right? So the common multiple between 8 and 3 is going to be 24. So I'm going to take the first fraction and, you know, multiply the top part of it and the bottom part of it by 3. And I'll use some colors here to help, because 8 multiplied with 3 will get me to 24. So I'll change the top as well. Minus, that's 2z plus 1. And that new denominator is a 3. And we'll multiply this one by 8, right? Because that'll get me my 24 in the denominator like I need. So we'll get 3. You know what we'll do is we'll actually distribute and multiply here. Because when I multiply each of those fractions, really it's like doing a distributive property. And then I can actually simplify the terms. So we'll end up with, maybe I'll keep it color-coded for now, 24z minus 9. And minus, and then we've got our bracket, because the subtraction sign makes a big difference in terms of negative. So inside that set of brackets, we're going to have 16z plus 8. Okay, and our denominator of 24. Now we can start to simplify, so we can break that negative off that set of brackets, we can expand, and then collect our like terms. So 24z minus 9 minus 16z minus 8, whole thing divided by 24. So you'll end up with, that looks like 8z minus 17 divided by 24. And again, there's no way to simplify this. Each of those terms, 8z, negative 17, 24, they don't share a common number, so I can't divide them and reduce this. So I'm done. Again, common denominator. You could expand the top if you wanted, collected like terms to make it as simplified as possible. And you can do something similar with the one beside this. So at any point, if you do want to just try something, just, you know, give it a pause, and then you can check the key in the links, just like always. So there's my two fractions. Again, common denominator needed. If you look at the coefficients of the denominator, one's a 4, one's a 6, so 24 would be a good number to get to. 12 is also another option. It's a little bit smaller than 24, so that might help in, you know, cutting some of the work down where you don't have to reduce things at the end. So we'll try to get them to 12. And then x squared is the highest power of my variable. So 12x squared is going to be what we're trying to work towards as a denominator. So we've got an x minus 2 already. We've got a 4x squared already. And we said we wanted to make it 12x squared, so we'll multiply both top and bottom by 3. For the second fraction, we've got an x plus 6, and we've got a 6x. And we want to again make this to 12x squared, so multiply both numerator and denominator by 2x to make this work out. And then we can start to simplify. So with our first fraction's numerator, we're going to end up with 3x minus 6. And then we'll have our plus sign. And then I don't need to worry about the negative here, so the brackets can freely disappear. And we'll get 2x squared plus 12x. Denominators, 12x squared, like we want. Combine all those like terms to finish this, and you'll end up with 2x squared plus 15x minus 6 as your numerator, divided by 12x squared. You know, for now we'll leave it just like this. Right? And I know that people's alarm bells are ringing when you see one of those trinomials on the top with an x squared, an x, and a constant. Well, the one thing that we did to really start this course off is, with quadratics, we factored some things. And if I can factor them, and I see the same factor top and bottom in a fraction, well, I know that they're going to simplify with each other, and, really they're going to simplify to 1, right? Because division of the same factor gives us a 1. And this is where, like, that talk of all those non-permissible values comes back, which we really haven't been talking about too much in this, because really we're just trying to focus on, adding and subtracting some fractions together. We can talk about the non-permissible values for sure, but we've talked about it in that first video there, and we aren't really asked to state them as we go through this. Really, we're just thinking about, simplifying these expressions and putting those fractions together. If you do think about this for this one, though, if you look at the original question, one denominator is a 4x squared, so I know x can't be 0 in the first fraction, and I also know the second fraction, same thing, x still can't be 0, because if x is 0, well, then I have a division by 0 situation, which is a no-no for math. So if I really want to include this, well, I know that x cannot be 0 as a non-permissible value. Right? All of those things are still true. Right? What happens if I'm putting together 3 fractions? Do any of the rules change? Well, the answer is no, right? I still need a common denominator to do this. I just have 3 terms to think about. So think about the numbers 3, 6, and 2. Well, the common number between them is 6, so that's good. If I think about my variables then, a cubed, a squared, and a, well, I'm going to pick the highest power of them. So I want my common denominator here to be 6a cubed. Right? That's the goal. And I can get each of these fractions to become 6a cubed by multiplying each respective fraction by something differently. So it really depends on what my denominator was to start with. So for the first one, if I'm trying to get to 6a cubed, let me move this over a little bit. Well, if I'm trying to get to 6a cubed, I need to multiply by 2, because 2 multiplied with 3 would give me that 6, so the first fraction is taken care of. In the second one, the only thing missing to get to 6a cubed is a factor of a, so I'll multiply a top and bottom. And then for the third and final fraction, I need to get to 6a cubed, so I need to multiply by a 3a squared, top and bottom. Right? As long as I change each individual fraction to get me to the same denominator, I'm still okay. So we can do this one step at a time. So this works out to be 8 over 6a cubed plus a squared over 6a cubed minus 15a squared over 6a cubed once again. If you actually do the subtraction, and then you could like reorder the terms if you even want to, you'll end up with 8 minus 14a squared, whole thing, divided by 6a cubed. Now this one is a little different in terms of the simplifying, because if I have 2 terms on the top, one of them is 8, the other is that negative 14a squared, one term on the bottom of 6a cubed, each of their coefficients are even. Right? So I can reduce those coefficients by a factor of 2 to end up with 4 minus 7a squared over 6a, not 6a cubed, 3a cubed. Now you might be wondering, well, why can't you divide the a's, top and the bottom? Right? And I can't, because both terms in the numerator would have to have a's to be able to divide them. Right? The only way I could simplify this is each of those coefficients of 8, 14, and 6. Each of them had a factor of 2 inside, right? But not every term has a factor of a inside, right? So I have to make sure that it was all 3. It's all or none situation. Okay, so I can still do that, and I can even do it with, a more complicated one with maybe there's some binomials on the top. Right? So think again about your common denominator first. That's the key. 4, 3, and 6, the common multiple is 12. I can get to 12 in all of them. Highest exponent on the variable will also be required. So 12w squared is the goal here. Okay, so I've got w plus 3 right now. I've got 4w squared right now, and I want to get to 12w squared, so multiply top and bottom by 3. Second fraction, w minus 1. There's a 3w. Again, I want to get to 12w squared, so 4w is required. And plus, there's a w plus 2. Here's a 6th. Again, 12w squared, so 2w squared is what's missing. Okay, and I can multiply each of those out and then start to simplify. So, yeah, let's multiply. Okay, so 3w plus 9 minus 4w squared, and maybe we'll keep this in brackets for now, minus 4w plus 2w cubed plus 4w squared divided by our 12w squared. Okay, so numerator can get simplified one more step. I've got a negative sign in the brackets to deal with. So I get 3w plus 9 minus 4w squared plus 4w plus 2w cubed plus 4w squared, whole thing divided by 12w squared. If you look at the numerator, the 4w squareds, positive and negative, they will simplify to 0. They create that 0 pair. Everything else can get added together to finish this. So we'll go in decreasing exponent power, so 2w cubed, no squares, and then you've got a plus 7w plus 9, whole thing divided by 12w squared. Alright, so there it is, your most simplified fraction for this. So again, common denominator is the key, then you can start to put everything together. Well, what happens when you've got binomials on the bottom too? Does anything really change? And well, kind of, slightly. Now you really got to think about quadratics again. You really got to think about factoring and how all of those rules came together. Right? I got to remember that, if I'm going to multiply something, I have to think about, distribution between binomials and, what that means when you go to cancel some terms out, they simplify to 1, or they, create 0 pairs, they simplify to nothing. I really got to remember factoring here. It is the key to this whole unit. So think about x squared minus 9. It's a special polynomial that we keep coming back to, and really it's a difference of squares. And I could factor it by taking the square root of the first and last terms and writing them, each of those factors, with differing signs in between. So if I break it down into its parts, really the first fraction is missing something. It's missing a factor of x minus 3. And I need that in there to make that common denominator. So the first fraction needs an x minus 3 factor, both in the numerator and the denominator. It already had the x plus 3. Right? But now they have a common denominator. When you think about the non-permissible values, well, it's 3 and negative 3. There's two places where it could potentially give me a 0 in that denominator. So I have two non-permissible values. But now I can start to simplify this. And the first fraction turns into 5x minus 15. There's a plus 2, but my denominator is really x squared minus 9. Now you can leave it in the factored form, like we've talked about before. It's helpful just to see those non-permissible values, so we'll leave it, and we won't expand it back out. And we already did all the work in factoring it, but we'll just simplify the numerator a little bit. 5x minus 13, and you've got your x minus 3x plus 3 in the denominator, because that's how I'm going to know that my non-permissible values are 3 and negative 3. Right? If I were to multiply everything back out, collect my terms, in x squared minus 9, it's a little harder to tell what your non-permissible values are going to be. The factored form is much, much better for this. And usually you'll see your denominator left in factored form, but your numerator will always be multiplied out with the terms collected. So you might have a trinomial or a binomial on top, but you'll have it in factored form in the denominator, usually, depending on what you're asked for when you approach a problem. Now, the same thing is true is maybe they're not a difference of squares, but maybe you have, two completely different factors. It's possible, but the same rules apply. I still need a common denominator, so think about what's missing from each fraction. Well, the first one, I've got a p minus 1 in the numerator, a p plus 2 in the denominator, but the other fraction, the second one, has a p plus 3 in there as well. So if I think about actually multiplying that first fraction by p plus 3, both numerator and denominator, well, I can do something similar with the second fraction, in the sense that, well, and I've got a p plus 2 to begin with, a p plus 3, so I'm going to multiply the second fraction by whatever the denominator of the first one was, so p plus 2. And that's going to give me the common denominator that I need. And again, you can think about your non-permissible values here again in the sense that they come from the original. So one of them, p can't be negative 2, so that'll zero out the denominator on the first fraction. P also can't be negative 3, that'll zero out the denominator on the second fraction. So again, I have two non-permissibles here, which I can still see when I multiply them out. They just happen to be part of both fractions now. So I can still simplify and do all of the things I did before, but we're going to leave the top part. No, actually, we're going to multiply the top part out, sorry. And we're going to leave the denominator in that factored form. Right? So I can really make sure that I see those non-permissible values. Okay, now, you might be tempted to just start canceling some things out, but again, don't, because the rules don't work the same here. If I wanted to simplify a p plus 3 from the denominator, it would have to be present in really every term here. Same thing for the p plus 2 in the denominator. Since it's not in both terms in the numerator, right? I don't see it on that left term to the left of the addition sign. I can't start to simplify by crossing things out. So I'll multiply everything out on the numerator side, leave the denominator in that factored form. So we're going to get a p squared minus 1p plus 3p, so plus 2p's minus 3, and then plus p squared, that's a perfect square, so p squared plus 4p plus 4. By simplifying the numerator, you get 2p squared, so collect those like terms, plus 6p's plus 1, whole thing divided by that common denominator, p plus 2, p plus 3. So I can do all of the same things that I could with regular fractions in the sense that they were just rational numbers. All of that is still true with, rational expressions, with variables. Okay, you may have to remember how to factor things. You may have to remember your exponent rules, which is why we always front load those in Math 10, because they just come back repeatedly again and again and again. That takes care of lesson 3. So this is adding and subtracting part 1. But when we take care of part 2 in the second, part 2 I guess inherently means the second one. So the fourth lesson, actually, the next video, you'll start to see denominators that might be trinomials. They might be a little bit more complex than some of the ones we've talked about to date. So you'll find that linked up above. Links to all the solutions and blank notes you'll find in the description as always. So until next time, enjoy the rest of your day and take care of yourselves. We'll see you next time.